Let's dive into a hidden world, an invisible landscape of energy that, believe it or not, governs pretty much everything around us. From the lights in your room to the screen you're looking at right now. We're talking about the world of electromagnetism. So let's start mapping it out.
So right off the bat, how do we even begin to understand forces we can't see? I mean, how do you map a landscape that's completely invisible? Well, it turns out physicists have this incredibly powerful tool for doing just that, a concept that lets us visualize this hidden world. And that concept is called potential.
Okay, to get started, I want you to imagine an invisible hill. This isn't a hill made of dirt or rock or anything like that. Nope, it's a hill made of pure energy. This is going to be our main analogy for getting a handle on electric potential.
So what is electric potential? You can think of it as electrical potential energy. It's not the energy of something moving, but the energy an object has just because of where it is in this invisible landscape. It's kind of like a topographical map, you know? But instead of showing altitude, this map shows energy levels all around us. And the rule here is super simple. The higher you are on this energy map, the more stored up energy there is. A charged particle at a spot with high potential is like a drop of water at the very top of a huge waterfall. It's not moving yet, but it is just loaded with the potential to create a massive flow.
But here's where it gets really interesting. A ball just sitting at the top of a hill, well, it doesn't do much on its own, does it? The action, the exciting part, happens when it starts to roll. In our electrical world, that rolling is what we call current, and it's all about the difference in height. Let's see how that works.
And this, right here, just illustrates that connection perfectly. The height on our make-believe hill, that's the electric potential, which we measure in volts. The ball we're imagining, that's an electric charge. And the motion, the ball rolling downhill, you guessed it, that's the electric current. The difference in that height, what we call voltage, is the whole reason the ball, the charge, moves in the first place.
So this is the really crucial point. Current doesn't just happen for no reason. It needs a push. First, you need a high potential. That's the top of our energy hill. Second, you need a low potential, a bottom for it to roll towards. The difference between those two spots is the voltage, and that's what provides the push that makes the charge roll from high to low. And that flow is the current. Simple as that.
All right, so we've got our invisible hill. Now let's add another feature to our invisible landscape. If electric potential is a static hill, then the magnetic field is more like a dynamic, flowing river. It's the other, equally important half of our electromagnetic world.
Now, unlike the simple height of electric potential, a magnetic field is what physicists call a vector field. That sounds complicated, but all it really means is that at every single point in space, the field has both a strength and a specific direction, just like the current in a river. It's literally a flow of force. But how in the world can we see this invisible river? Well, you've probably seen this classic experiment. When you sprinkle little iron filings around a magnet, they don't just fall randomly. They actually trace out these beautiful, elegant, curved lines. It's like they're showing us the secret. It's a natural visualization method revealing the invisible currents of the magnetic field. So we've got our energy hill and our force river. It might seem like two completely separate ideas, right? But the real mind-blowing breakthrough in physics was realizing they aren't separate at all. They're just two different ways of looking at a single, unified, fundamental landscape.
Now, to map this whole unified landscape, physicists use two main tools. The first one is that electric potential we talked about. That describes the height of our energy hill. The second one is a bit more complex. It's called the magnetic vector potential, and it's basically the map that describes the flow and the shape of our magnetic river. Okay, now don't let these symbols freak you out. We're not about to do a math class, I promise. Let's just focus on the story they're telling. This is like the secret code that connects our entire invisible landscape. The first rule tells us how the magnetic river gets its shape and flow. But that second one, that's the real game changer. It shows that the electric hill and the magnetic river are totally connected. A change in one directly causes a change in the other. It's one single, interconnected system. You know, this might all seem a bit abstract, I get it, but understanding this invisible map of potential is absolutely critical. It's not some clever analogy. It's the actual language physicists use to describe the fundamental forces that built our world. So what's the big takeaway here? It's the sheer power of this one idea. Potential is the underlying map that governs not just electricity, but magnetism too. And that connection, the one described in those equations, that's what gives us everything from radio waves to light itself.
And this isn't some old dusty idea. It's foundational to modern physics, from quantum mechanics to relativity. It gives us a real way to see the unseen.
And that leaves us with a final, kind of wild thought. We've just mapped the invisible landscape of electromagnetism using this idea of potential. But it really makes you wonder, what other invisible maps, what other fundamental potentials might be out there, quietly shaping the very fabric of our universe?